Hello students, welcome back. So we are in chapter number 4 and this is about the chapter number 4 about transient vibration. Okay. So we have already learned if the force is one impulse in form of impulse of a force. So let us say the force is, let's call it F hat divided by del epsilon, or del tau, we can say del tau, so this is T, del tau. So distance from here to here, del tau, let us say. So if this kind of force is there, okay, then what kind of response it will have. So of course the impulse of the force is given by equal to F, the area, right? So area of this is impulse of the force, so F hat divided by del tau times del tau equal to F hat. So F hat is impulse of a force, which is a force multiplied by time basically. This is what that is, yeah. If this kind of force is applied, we also represent this as F equal to F hat delta T minus tau. So if from here to here, this is tau, right? So this is force like this, yeah. So given this force, this impulse of the force, a small force applied for very small amount of time, okay. So we represent mathematically as F equal to F hat del T minus tau, and the meaning, how the force looks like, how the force distributed over time is like this. F hat divided by del T is the magnitude of the force, and it lasts for del tau time del tau, right? So for this, we have seen that if you apply this force, the solution that you get is equal to, let's call it the solution for this one as x hat t. What we got? We get F divided by m omega n sine omega nt. That's what we saw. Okay. Yesterday we used F naught instead of F hat. Yeah. However, remember the meaning is different. Okay. When you in the second case, for the step input, we took F naught there also, but F naught there meant actual force, not impulse, not force multiplied by time, not area of the force versus time plot, not that. Actual force, F naught has a dimension of force or units of force. In this case, F hat has a dimension of force multiplied by time or area under the curve of force with respect to time. So this we know, given the force as an impulse or in terms of delta direct function, what would be the solution? Again, remember this solution, actually this solution what we found is not for F hat del T minus tau, okay? This one for this, for F equal to F hat del T, for this we found out the solution, okay? So given F equal to F hat del T, this is the solution. For this one, solution will be shifted by T by T. So solution will be in that case, what will be the solution in that case? Will be, for this one, solution will be simply x hat T minus tau, right? So that really means this will be equal to 0, okay, for T less than tau, and will be equal to F hat m omega n sine omega n t minus tau for t equal to greater than c. This is how the solution we will find out, right? You just shift it. Since this is the solution for when tau equal to 0, and when this, if the time is given, in this case the force was given right at t equal to 0. In this case, force is given at time equal to tau. If you know this solution, for this solution, let us say our answer is like this. For this one, solution will be wherever the force is, from there the solution will start. So this is shifting. You have shifted by tau, and this is what is appearing here. Okay, this much you should have very clear idea about it. Okay, so why we have t minus tau terms appearing here? Because we are going to use this. Okay, what I mean to say is, if you know a solution for an impulse, you can find solution of any kind of force. Okay, and that's what we will see here. Okay, how can we use this solution to find out a solution for any type of force applied? We have used different kind, right? So we used, for example, mx double dot plus cx dot plus kx equal to any kind force we apply. We know if you apply the Laplace transform, and let us say regardless of what you have, there may be some value x0 equal to x0, let us say x dot 0 equal to v naught. You may have all those things, and then also you can find out simply what you take the Laplace transform both the sides, and then you take inverse Laplace transform of whatever you get, inverse of that will give you xt. So this method we know, very powerful method. Given any kind of force here, yeah, can find out the solution for sure. We know that. However, we also want to understand one very good thing about the impulse response and how this can enable you to find solution of any kind of force given. And we will come back to this also, yeah, and then we will see what is the meaning of that, how it fits there. And all these things are very important also for your control engineering, yeah. So there we will see like the impulse response, how it is related. So that time also we will come back here. Here we are studying just the vibration system, a spring mass damper system. There it could be any kind of system. That is the only difference. But it is very important to understand that. Yeah. Okay. So let's first understand, if any kind of force is given, then how we can interpret it differently. So this is T, this is F, and let us say any kind of force is given like this. Yeah, this arbitrary force Ft, right? This is Ft given for us. Okay. Now what we are going to do? We are going to consider one strip of it, very, very small. Distance from here, distance is tau. This width is d tau, like this. Okay. Now, the shaded area, this one is you can consider that an impulse of a force, right? So corresponding this one, impulse of force, corresponding impulse of the force will be from here to here, this is F. So since this is Ft, that really means from here to here, actual width here to here will be force at time tau. So this will be F tau. Impulse, force impulse, the impulse is given by force multiplied by time, and here force is F tau, F at t equal to tau, multiplied by time, so d tau, like this. Okay, this impulse of the force right here, how will we write mathematically this one, right? This is at t equal to, so impulse of a force at t equal to tau is like this one. Mathematically, we can also write F hat, right? Here F hat we wrote. So F hat is for us is equal to F, we write T, or we can write like this, F tau d tau, and then we will have delta t minus tau. The same notation we used yesterday, right? So this you can write it as F naught, for example, right? This is yesterday, this we used as F naught. So actually this is F at tau multiplied by d tau. This is the impulse. This we used yesterday. We use like this. Yeah. Okay. So we have here this F naught. Yesterday we used at F naught, but actually this is F hat. Yeah. So given this one, for this force, if you have to find out the response, how will you find out? Yeah. So we know that if given this force, the corresponding displacement is x hat is equal to, what was that? Yesterday we had found out F naught over m omega n, and then we had sine omega nt. Yeah. So what is F naught? F naught here is F tau d tau, right? And then F tau d tau divided by m omega n sine omega n. What is the value here? This will be for t minus tau, right? Okay. Why t minus tau? This is because our time, basically this one, this displacement will be 0 till here, and displacement will start corresponding since the force is applied here, so displacement will start here. Hence sine omega n t minus tau, meaning that sine t minus tau equal to 0 if t less than tau, and equal to sine t minus tau if t is greater than equal to tau. So this is what the meaning here is. Yeah. So what we found out here is the response because of this impulse. Yeah, and that impulse, because of one impulse, we found out the solution here. Yesterday we found out this one. When force is given, this solution is for F equal to F naught delta T, and this solution is for this one. This is for F hat equal to F naught this solution is simply for this. Okay, for this F hat we have, right? So because delta T minus tau is here, hence we have this term appearing here. This really means that this force is at, although it gives you the F tau times d tau gives you the area, yeah, and however this is how the area is how it is distributed, and this kind of force is at T equal to tau, and this it tells you this is at T equal to tau, hence your displacement also starts from here only, before that it's 0, and hence you have T minus tau term here. So it's important that you understand it. Okay. Now next, for any kind of force, Ft is general force, arbitrary force, and for any kind of force we have to find out the solution, then how to do it. Okay, so let us let's find out the solution when we have a general purpose force like Ft. Then what happens? Now if the force is F tau d tau del T minus tau, then the solution is F T d tau over m omega n sine omega n T minus tau. Let us say we want to find out the solution here somewhere. Okay, this is our time, arbitrary time T, right? Then what will be the solution? How will we get the x? Xt means general solution, x at time t will be simply integration of this term. Yeah? So this contribution, this displacement contribution comes from this force. Yeah. So in a way, this one is something like actually dx basically. This is nothing but something, it is dx basically. Yeah. This really means x hat is because of a force impulse for impulse F naught. But this is also a contribution of this strip of the force. So this one from here to here you can say contribution of force at time tau. Contribution to what? Contribution to xt. Yeah. So we are right now just considering the force here, that's it, nowhere. And for this force, a small, the force F tau, which is being applied for very small time d tau, and then for that force only, for that impulse only, the solution is this much. If we consider all of them, means we have lot of strips there, right? Lot of impulses, all combined together. Then we have to integrate. We have to take the contribution of all of them. Sum of contribution due to force impulse from t equal to 0 to t equal to t, right? So that's what we have to find out, okay? So sum of the contribution. So how do you do? We will integrate this. So we already have this one. So we get f tau divided by m omega n and sine omega n t minus tau and d tau. So this is what our xt is. Yeah. Okay. How it looks like? This looks like what is called convolution. Convolution. Yeah. We can say from here to here is a small f small f tau equal to big F tau divided by m omega n, and we can write this xt is equal to from 0 to 0 to t. So since we have defined this function from 0 to infinity, okay, this everything is 0. The force is 0 before here this side at t equal to 0. Force starts before that, the force is 0, and hence we can also integrate from 0 instead of from minus infinity. So from 0 to t. So xt we also write it as f. This is a function basically. We f star, and this is one. This is f. Let's call it g. Yeah, this is g t minus tau, right? So we will call it f star g. This is a convolution of function f and g. Yeah, and then this is a function of t. Yeah, so basically let's write it here. So convolution means f star g. T means typically it could be 0 to t or 0 to infinity. Let's write 0 to t only. So 0 to t, and then we have f times tau times g t minus tau, and here you have d tau. It's also called convolution, and this is how it is denoted. Okay, this we will be using. Okay, so this in controls and vibrations, it has a very good meaning, and it is very important, very powerful statement actually, and we will see that, okay, when time comes. Okay. Okay, now xt will be simply equal to 0 to integration 0 to 2. Here f is the any arbitrary force, function of tau divided by m omega n. Omega n is no root k over m. Okay, then sine omega n t minus tau d tau. Remember, this solution we got for what? For a spring and mass system only. Okay, so this is for a, okay, so this solution is for a spring and mass system only. Yesterday we were working on that. If we had a spring damper system, this solution will change. You can see here there is no zeta term, there is no c term. We have k over m term, right? Omega n equal to root k over m. So we had omega n terms, but we don't have any zeta term. So solution, this we got for a spring mass system only. We are trying here a spring mass system so that it's easy to understand, and then we can extend that to a spring mass damper system as well. But here just we have taken a small example. So what we have done is, for a given impulse, whatever the solution is, we have applied to get the solution for any arbitrary force function expressed in terms of time. And what we have done, it is simply the convolution. Convolution of what? Convolution of force to the x hat. Force to the response due to impulse. Response due to impulse. Yeah. So this convolution has given you the solution, basically. Yeah. And we will apply that. We will apply that to find out the solution that you got yesterday. For example, yesterday we solved what is the solution if there is a step function. So let's apply this one and let's find out whether it solves the step function. A step function, we have applied what did we do yesterday? We applied the Laplace method directly to find out the solution for the spring mass system for a given step input like this. But now we know the force is like this one. Can we apply this method, new method that we learned today to find out the solution because of this step input, the step force input? Okay, that's what we will do now. Yeah. Okay. So far, for a spring mass system, yeah, and what we get? We have the solution for any kind of force Ft. We can write xt as 0 to t, and then we have f tau, then we have m, we have omega n, then sine, then we have t minus tau d tau. So this is we are saying if any force you put here and you integrate, you get the displacement because of that force. That's what we are saying. Okay. Now take example. Initial solve example. An example is force is given like this, T, and this is F, and force is like this. At T equal to 0, we have F naught here. Right? So as I wrote yesterday, F equal to F naught and unit step function ut. Yeah. So F is given like this. We are saying a xt equal to 1. And yesterday we solved. Yeah. But different method. We apply the Laplace method. Today we are going to apply this convolution method. Yeah, or impulse response method. It is something like, let us say, you have to find out for let us say sinusoidal, the response because of a sinusoidal input, let us say. Yeah. And you have given a structure, and for that you have to find out the response. Then what do you call? What do? You have a hammer and you just struck the structure with your hammer. That is something like impulse force. And then you record the displacement. So whatever displacement is, just record it and that's it. If you have that, then if you can go and use your computer to find out exactly how it will behave under any kind of force, including sinusoidal force or any triangular force or a square wave, any kind of force, how it will behave, you can find out. That's what the meaning is. It is so powerful. For experimental purposes also you can use, actually. Yeah? Like for example, for breeze, you have to find out how it will behave because of some kind of wave, and that wave may be because of anything, because of water or because of wind, anything, right? So how will you find out? What you do, basically, it is just, although it looks like theoretical, but let us say you have a big hammer, you have struck the breeze, you record the displacement, and then you know that is the solution for an impulse force. So then you can do convolution like this one to find out the solution because of any kind of displacement. It could be for sinusoidal displacement or triangular wave or trapezoidal wave or any kind of wave we can do. Okay, now let's apply this here, and then for that we can find out xt is equal to, and then you have 0 to t, and then here is f is f naught ut. So basically, since t starts as 0, so you can write f equal to f naught directly. So basically this is a constant, this is f naught, so we write f naught here, divided by m omega n. So right, then sine, then t minus tau t tau. So this equal to f naught for t greater than equal to 0. Right? So you can write like this. So it is basically f equal to f naught only, because ut starts right at t equal to 0. Right? So we can write like this also. So this is the solution what we are getting, xt, because of this one, right? Okay. So we get 0 to t, and then we can take this outside. So we have f naught divided by m, then omega n, 0 to t sine t minus tau d tau equal to f naught over m omega n, and this, what do we get? This will be cos, and then this will be minus cos, of course, and then t, this will be omega n here. So solution will be here omega n. So okay, there are these are not correct. So sine omega n times t minus tau. So omega n sine omega n. So this becomes minus cos omega n t minus tau, and divided by, so tau has minus omega term here, so we have minus omega n terms divided by that, right? And then from t to 0, and hence we get xt is equal to f naught divided by m omega n. Take omega n here, so we get omega n square, and then minus plus, so you have simply cos omega n t minus tau, and from t to 0 equal to f naught m omega n square, and here you put t here, to t minus t 0, so it becomes 1 minus 0 here, so it becomes cos omega n t. Okay, this is what the solution we got yesterday. We got exactly this. We got xt equal to f naught over m omega n square 1 minus cos omega n t, where we know that omega n square equal to k over m, or that really means k equal to m omega n square, hence xt equal to f naught divided by k, and then 1 minus cos omega n t. Right? So this is the solution yesterday we got for a step input. The same solution we are getting today, okay, but different method. Yeah. So this is a of course this also mathematics, that was also mathematics, but here it has more physical meaning. Yeah. So here we are looking at the force, and then we are seeing the contribution of each moment, basically, right? For each moment, you know that for each moment there is a vibration produced, and each moment the vibration will be given by like this one, and hence we are integrating over the full period of application of time, and then you get the value of this force, right? Value of this displacement. Okay. Let's apply to like a ramp force. Okay, let us see. We will apply the same thing. We will see what kind of solution we get. One thing also we should notice that when we had applied F force, which was equal to F hat equal to F naught delta T minus tau, or since it is starting at t equal to 0, so delta t, and then we got the solution, which was x hat was equal to F naught over m omega n sine omega n t. Now, if the unit impulse, right, you can use unit impulse. So for unit impulse, we have F, let's call U like this, unit impulse, equal to 1 delta t, right, or simply this is delta t only. And then we have x hat for unit impulse will be equal to, now we have just 1 here, 1, right? So F naught is 1, so this will be 1 over m omega n and sine omega n t. So this is the response of a spring mass, or you call unit impulse response of a spring mass system. So we say like that. So this is a unit impulse because F naught is equal to 1. Yeah. This will be more relevant in control system. Okay. So I'm also preparing you for control system. So all those things, terms which are appearing here will reappear there. So next is what we want. For us, force is given. Force equal to, let us say, force equal to alpha times t. Okay. What is the meaning of that? Means force is given like this, goes like this. Yeah, this is F, this is T, and this is what the force is moving. Slope is, we have the slope. Slope is angle, the tan alpha. The slope is, in this case, is F is proportional to that, so df over dt equal to alpha or tan alpha. The alpha is the slope, basically, right? Tan alpha. Okay. So in this case, if this is given like this one, then we have to find out xt, and xt equal to what? Yeah? Okay. Now, the alpha is rate of change of time in this, here the slope means rate of change with respect to time. So this is f dot equal to alpha, and hence the slope or df over dt is alpha. Okay, so so alpha is the value which is equal to tan theta, right? So theta value will be here like this, right? So yeah, just to clarify. Okay, so basically this if we have to find out the displacement because of this force, and how to find out, we already have for 1 we have like this, and we have already derived earlier, and what it says, the earlier force we had simply x t is equal to, and what did we have? We have 0 to t, then we have force, any arbitrary force, tau divided by m omega n, and then we have sine omega n t minus tau and d tau. So this is the solution. Yeah. Or simply you can recognize this is also like this, 0 to t f tau multiplied by 1 over m omega n sine omega n t minus tau d tau. So force, and this is the unit response, right? This is the unit impulse response, and this is the force term. That means this represents actually convolution of two things, force and unit impulse response. Hence unit impulse response is important, right? So that means xt is given by, is a convolution of force and unit impulse response. As simple as that. You can write xt equal to convolution of force and unit impulse response. That means if you know the displacement because of unit impulse, then you convolute with the force itself, expression for the force, you get xt. Yeah. So if that really means xt is equal to 0 to t, then f tau, and this is x hat u, right? X hat u t minus tau d tau. That's what it tells you, right? This is what the meaning of that is. Yeah. So this is how you do it. Anyway, coming back here, this is the bigger picture. Yeah. So this is valid for any kind of system, right? Here, for us here, unit impulse response for a spring mass system. But if you know x hat u for any kind of system, it may have damper or more complicated. Then also, as long as it's linear, this is also, remember that this is all valid for linear system only. So if we have unit response, the unit impulse response for any kind of system, you convolute that, and then you get the xt for that system. Current system is a spring mass system, and for that we have to find out the response because of f, and we can do by integrating this one. So we integrate further. So xt becomes equal to 0 to t, and f tau is what? F tau is alpha tau. So we write alpha tau here. Then we have 1 over m omega n, and then sine omega n sine, then omega n t minus tau d tau, okay, is equal to, just matter of integration now, we just integrate, you get the value, okay. So but we will integrate further. So we get alpha divided by m omega n 0 to t, and then we get tau, then we get sine omega n t minus tau d tau, okay. Now just matter of integration, I said earlier. So let's find out what the value is. Okay, so continuing from here, so we get xt is equal to, and then alpha divided by m omega n, okay, and then we have this value, okay. So integration 0 to t, and then tau times sine omega n t minus tau. So we can write like this, t here, and then here this one we can write it like this, d cos omega n t minus tau, right? Okay, why we can write like this? Because if you differentiate it, what do you get? You get minus sine omega n t minus tau multiplied by omega n, right? So we can write omega n here equals like this, okay. So if you differentiate this one, then what do you get? Here I'm just writing differentiate this one, so you get minus sine omega n t minus tau, and then you also get multiplied by minus omega n, okay, minus omega n. So this is multiplication. So minus becomes plus multiplied by omega n, yeah, and we divide by omega n, so we get the original sine omega n t minus tau. So this is correct. Okay. Okay. So that is equal to alpha over m omega n square, and then we have this 0, so t tau d cos omega n t minus tau, sorry, this, okay. I'm using integration by parts strategy, okay. So equal to alpha over m omega n square, okay, fine. And then we have here we will have tau cos omega n t minus tau, okay. So we have like this, so this value t to 0, then we have minus, integration by parts, okay. So integration by parts, okay. So what is that? This is like u dv equal to uv minus v du. So that's what we are doing, okay. So this becomes cos omega n t minus tau, and then we have d tau, again 0 to t, yeah, okay, it here like this, okay. Okay, equal to alpha over m omega n square, and this value, what do we get? This one is t here, so we get t, then t put here, so becomes 0, the cos 0 equal to 1, so t, we get just t, and here 0, this tau is 0, so everything becomes 0, so we get t here. In this case, what we get? Now cos n t minus tau, that is what? This becomes sine, so sine omega n t minus tau, and divided by minus omega n, yeah, so divided by minus omega n, and the t to 0, right, is the limit, and equal to alpha m omega n square, and we get t minus. Now we put it here, put t here, then what do you get? Sine 0, and hence you get 0. Now you put it, so first term t will give you 0, second term t we get sine minus, and we get sine t, sine omega n t, sine omega n t divided by omega n, right, like that. So we get alpha m omega n square t minus, here we have minus, okay, so minus here, so minus plus 1 over omega n sine omega n t. So this is what the solution we get, okay. The final solution becomes xt, or right, xt is equal to alpha over m omega n square. M omega n square is also k, right? You can also write m omega n square, instead of m omega n square you can write k here, t plus 1 over omega n sine omega n t. So this is the solution for the ramp input, yeah. And what we used? We used the convolution method, convolution with respect to the impulse, unit impulse response. That is xt, how we got? We can mathematically we can say this xt displacement equal to convolution of force with the unit impulse response. So mathematically, just one sentence that will explain this one. Okay, and similarly, any kind of force, any kind of system. Yeah, this is just example we showed. Yeah, any kind of system, any kind of force. When we say any kind of system, linear system, of course, and in terms of vibration, what I mean to say is right now we are doing it for mass and spring system. You can extend it to mass spring damper system. Yeah, and force arbitrary. So far we have seen for the step input means becoming constant force. Just you apply a constant force suddenly. Second is the ramp in increasing with time. Similarly, you can do any kind of force and still it's relevant. So now the question is, can we quickly apply the same thing to mass spring damper system? So damper system coming into picture now, right? So what we have to know? We have to know just the unit impulse response. Yeah. So unit impulse response. And how do you find out? We write the equation mx double dot plus cx dot plus kx equal to just 1, right? So delta t, that's it. Yeah, and then what we do? Or in fact, let's write it for any force ft like this. For ft, and we apply to the whole equation, and what we get? We get L, we have M, and then we have xs times s square minus x0 s minus s x dot 0 plus c, then we have xs times s minus x0 plus k, then xs equal to, let us say this is fs. So what is fs? Fs equal to Laplace transform of force function, right? So like this, yeah. Or we write, in this case, what are we assuming? We are assuming, okay, assuming x0 equal to 0 and x dot equal to 0, yeah, okay. And what do you get in that case? We get simply m s square plus cs plus k times xs equal to fs, and simply what we get? We get xs over fs, which is output over input, is equal to, okay, what do you get? We get xs over fs equal to 1 over ms square plus cs plus k. That's what we get. Yeah. Output over input is also known as transfer function. Okay, and we will see that in control theory. Yeah. Okay. So like this one. Now the thing is, when ft is equal to simply delta t, then fs equal to 1. Yeah, and hence Hence you know that xs simply becomes 1 over ms square plus cs plus k. That's it. Yeah. So that means xt, which is in fact our for unit response, so xu hat t, xu hat t for this a spring mass damper system becomes equal to Laplace inverse of ms square plus cs plus k, and which is equal to, if we find out, we have to also write in terms of this, so we can write 1 over m, and here we get s square plus we get 2 zeta omega n plus omega n square, right? So we get like that. Again, we will assume the system is underdamped, and hence we will have L inverse 1 over m. Okay, let's write down here. So let's write this term up. So here the unit impulse response becomes equal to L inverse of 1 over m divided by, divided by what? We have s square plus 2, so we can write s square plus like this, s plus, and then we have zeta omega n square plus we have omega d square, where omega d equal to omega n root 1 minus zeta square, and x hat u t simply becomes, from here if you look at that, we will get from this term we have e to the first 1 over m term, so 1 over m, then you have these terms, so e to the power minus zeta omega n, and then you have this term, right? So for this term you get sine, so you get sine, what sine? Sine omega d t, and of course divided by, you have since omega d here, so omega d will be here, so we get 1 over m omega d e to the power minus zeta, it will be t here also, so zeta omega n t, then we get sine omega dt. So this is the unit impulse response. So unit impulse response, okay, for a spring mass damper system. Okay, if you put zeta equal to 0, so automatically this will omega n becomes omega d, you get 1 over omega n, the sine omega n t, automatically this also goes to becomes the behave like a spring mass system. But this is for the spring mass damper system. This is what the unit response, impulse response looks like. So now for any force, your actual x will be given by the convolution of force with unit impulse response function. Right? What I mean to say is you can write simply xt equal to f convolution of f with x hat u t, yeah, where x hat u is given here, right? This is what is given here, and this is for the spring mass damper system. So this is always valid, as I said earlier. Earlier we had this one for a spring mass system only. Now for a spring mass damper system we have the new unit impulse response. Yeah, so now we have to do convolution with the given any arbitrary force with this one, and you get the solution xt. Yeah, okay. It's also interesting that if you apply the Laplace transform over, then what happens? Xt is equal to Laplace transform of f star x star u and t, right? Like this one. Yeah, and that becomes equal to, actually Laplace of this convolution is very simple fs times x us, simple multiplication. So basically x s equal to fs multiplied by simple multiplication, where x u s is the, so where x hat u s equal to Laplace transform of this x hat u t, actually. Yeah, okay. So from here, if that is the case, this equation, what do you get from there? From there we get xs over fs is equal to x us. Yeah, that means x us equal to xs over fs. This is output over input, that is transfer function. So that really means transfer function of a system is nothing but the Laplace transform of the unit impulse response. Right? That's what it means, right? So transfer function, that this tells us transfer function TF, transfer function equal to Laplace transform of unit impulse response. As simple as that. Yeah? Hence, you understand now, unit impulse response is so important and how much powerful it is. And hence, no doubt, it's very important for the controls part. We will see that. Yeah? So it is something like transfer function is the most basic thing which is most frequently term used in a control system. And this transfer function, you can just find out. Let us say for this one, I have to find out transfer function. What we do? I have a hammer. We just hammer it. Yeah. We find out the displacement. Okay. I recall the displacement, and I do the Laplace transform of that displacement. Yeah. I have the transfer function of this system ready, but I have to divide it by the intensity of the force, because the force had to be unit, impulse had to be unit. So divide by the actual impulse, and we get the transfer function for this system. Okay? So always I say, as before I have said, that to try to also understand the big picture, the physical meaning of this, not just get lost in the equations. Okay, that is all for this.